Hello everyone, I am Dr. Supriya Patil from Abasaheb Garware College, Pune. Let us begin with the module on logic families, its characteristics and types. In almost all the electronic gadgets, digital systems are used for their operation. These digital systems make use of digital ICs. In order to have the simplicity in the design and compatibility of logic circuits, these digital ICs must be from the same family. In this module, we are going to see the idea of logic family, its different types and electrical characteristics.
Learning outcome. After completing this module, you will be able to understand need of logic families, know the significance of logic families, identify different characteristics of logic families, classify the logic families, and study the evolution of different logic families. Let us define the logic family. It is a group of compatible ICs with the same logic levels and supply voltages for performing various logic functions have been fabricated using a specific circuit configuration. It is also a collection of different ICs that have similar circuit characteristics. The circuit design of the basic gate of each logic family is same. Significance of logic family. Generally, logic family is used because it reduces the complexity in the design of logic circuits. That is, it is simple to design. There are members with same electrical characteristics. There is no need of any complex interface circuits to match the current and voltage requirements of two logic circuits. It also ensures the compatibility of other logic circuits in terms of voltage and current levels. And of course, it ensures the proper operation of the circuit. And last but not the least is it is easy to expand. Logic families are classified according to the principal type of electronic components used in the fabrication. They are bipolar ICs, which uses diodes and transistors or BJTs, and unipolar ICs, which uses MOSFETs. Bipolar ICs are further classified into two types, that is non-saturated and saturated. In the non-saturated, they are further classified as emitter coupled logic and Schottky TTL, while in saturated, they are classified as diode logic, that is DL, resistor transistor logic, that is RTL, and diode transistor logic, that is DTL. Unipolar ICs are also classified as PMOS, that is P-channel MOSFETs, NMOS, that is N-channel MOSFETs, and CMOS, that is complementary MOSFETs. Out of the logic families mentioned above, DL, RTL, and DTL are not much useful due to some inherent disadvantages, while TTL, ECL, and CMOS are widely used in many digital circuit design applications. Let us consider different logic families and the components which are used in the fabrication of that logic family. DL, diode logic, uses diodes as the basic component of fabrication. RTL, that is resistor transistor logic, it uses resistors and transistors as the basic components. DTL, that is diode transistor logic, uses diodes, transistors and resistors as the basic components. TTL, that is transistor logic, uses transistors and diffuse resistors. Emitter coupled logic uses transistors and diodes. PMOS, that is p-channel metal oxide semiconductor logic, uses p-channel MOSFETs. NMOS, n-channel metal oxide semiconductor logic, uses n-channel MOSFETs, while CMOS, that is complementary metal oxide semiconductor logic, uses both p-channel as well as n-channel MOSFETs. Logic families are further classified based on the number of logic gates fabricated per chip in the IC form. SSI, that is small scale integration, has less than 12 gates per chip. MSI, that is medium scale integration, uses less than 100 gates per chip. LSI, that is large scale integration, has about 1K gates per chip, and VLSI, that is very large scale integration, has about 10K gates per chip. Positive and negative logic. Usually, this term refers to binary logic level consisting of two states, namely low state, that is 0 volt or logic 0, and high state or plus V or logic high. In addition to two-state digital circuits, some circuits are three-state or tri-state logic circuits. Third state or high impedance state is added in addition to two logic states, that is logic 0 and logic 1. If the circuit is in this state, it is effectively removing the output from the circuit. Every logic gate accepts inputs and produces output in terms of logic and voltage levels. There is a freedom to interpret logic and voltage levels, which leads to two types of logic configurations as positive logic and negative logic. Table shows two assignments that define positive and negative logic systems. Positive logic system uses H as equal to logic 1 and L as a logic 0, while in negative logic, H is referred as logic 0 and L is referred as logic 1. The binary signal at the input or output of any gate has one of two values except during transition. One signal value represents logic 1 and the other as logic 0. Since two signal values are assigned to two logic values, there exist two different assignments of signal to logic. Because of the principle of duality of Boolean algebra, an interchange of signal values assignments results in a dual function implementation. Consider the two values of binary signal as shown in the figure. One value must be higher than the other since the two values must be different in order to distinguish them. The higher level is assigned as H and the lower level as L. There are two choices of logic value assignment. Choosing the high level H to represent logic 1 defines positive logic. Choosing the low level L to represent logic 1 defines negative logic. It is not the signal polarity that determines the type of the logic, but rather the assignment of the logic values according to the relative amplitudes of the signal. Integrated circuit data sheets define digital function in terms of H and L and not in terms of logic 0 or logic 1. It is up to the user to determine the positive and negative assignments. In each family, there is a range of voltage values that the circuit will recognize as a high or low level. Physical interpretation of positive and negative logic. Integrated circuit data sheet define digital function in terms of H and L and not in terms of logic 0 or logic 1. It is up to the user to determine the positive and negative assignment. In each family, there is a range of voltage values that the circuit will recognize as a high or a low level. Consider the table to understand the logical interpretation of any gate. It is dependent on whether positive or negative logic is assumed. This table demonstrates how physical interpretation of logic gate changes with positive and negative logic implementations. A physical implementation of gate has two different representations depending on whether positive or negative logic is used. Positive logic inputs and outputs are also known as active high signals. Negative logic inputs and outputs are also known as active low signals. Input and output polarity may be indicated by bubble or no bubble. Figure indicates two different implementations, namely positive logic AND gate and a negative logic OR gate for same logic level implementation. Characteristics of logic families. IV requirements. Let us consider different characteristics of logic families. High level input current IIH. This is the current flowing into taken as positive or out of taken as negative an input when a high level input voltage equal to the minimum high level output voltage specified for the family is applied. High level output current IOH. This is the maximum current flowing out of the output when the input conditions are such that the output is in the logic high state. It is normally shown as a negative number. It tells about the current sourcing capability of the output. The magnitude of IOH determines the number of inputs the logic function can drive when its output is in the logic high state. High level input voltage VIH. This is the minimum voltage level that needs to be applied at the input to be recognized as a legal high level for the specified family. High level output voltage VOH. This is the minimum voltage on the output pin of logic function when the input conditions establish logic high at the output for the specified family. It may be mentioned here that for a given logic family, the VOH specification is always greater than the VIH specification to ensure output to input compatibility when the output of one device feeds the input of other. Low level input current IIL. The low level input current is the maximum current flowing into taken as positive or out of taken as negative the input of the logic function when the voltage applied at the input equals the maximum low level output voltage specified for the family. Low level output current IOL. This is the maximum current flowing into the output pin of a logic function when the input conditions are such that the output is in logic low state. It tells about the current sinking capability of the output. The magnitude of IOL determines the number of inputs the logic function can drive when its output is in the logic low state. Low level input voltage VIL. This is the maximum voltage level applied at the input that is recognized as a legal low level for the specified family. Low level output voltage VOL. This is the maximum voltage on the output pin of a logic function when the input conditions establish logic low at the output for the specified family. Now let us consider different electrical characteristics of logic families. Let us start with the fan out. It specifies the number of standard loads that the output of the gate can drive without affecting its normal operation. A standard load is usually defined as the amount of current needed by an input of another gate in the same family. It is shown in the figure. Sometimes the term loading is also used instead of fan out. This term is derived from the fact that the output of the gate can supply a limited amount of current above which it ceases to operate properly and is said to be overloaded. The output of the gate is usually connected to the inputs of similar gates. Each input consumes a certain amount of power from gate input so that each additional connection adds to load the gate. These loading rules are listed for family of standard digital circuits. The rules specify the maximum amount of loading allowed for each output in the circuit. Exceeding the specified maximum load may cause a malfunction because circuit cannot supply the power demanded from it. Thus, fan out is maximum number of inputs that can be connected to the output of the gate and is expressed by a number. The fan out capability of a gate must be considered when simplifying Boolean functions. One should use non-inverting amplifiers or buffers to provide additional driving capabilities for heavy loads. The delay offered by a gate increases with increase in fan out. Fan in. The number of inputs of logic gate is defined as fan in. It is decided by the input current sinking capability of a logic gate as shown in the figure. Power dissipation. It is power supplied required to operate the gate. This is expressed in milliwatt, that is MW, and represents actual power dissipated in the gate. It is the number that represents power delivered to gate from power supply. The total power dissipated in the digital system is sum of the power dissipated in each digital IC. Power dissipation is determined by the current ICC that the IC draws from the VCC supply. It is given by P in milliwatt, that is power dissipation, equal to VCC, which is the power supply voltage, into ICC, that is the current demanded by the IC. ICC is the average value of IC0 and IC1, that is the current demanded at logic 0 and current demanded at logic 1. Power dissipation alpha is the heat generated by the system. Excessive heat dissipation may increase operating temperature and cause gate circuitry to drift out of its normal operating range. Electrical characteristic of logic family. They are rise time TR. This is the time that elapses between 10% and 90% of the final signal level when the signal is making a transition from logic low to logic high. Fall time TF. This is time that elapses between 90% and 10% of the signal level when it is making high to low transition. Propagation delay. The propagation delay is the time delay between the occurrence of change in the logical level at the input and before it is reflected at the output. It is the time delay between the specified voltage points on the input and output waveforms. Propagation delays are separately defined for low to high and high to low transitions at the output. In addition, we also define enable and disable time delays that occur during transition between the high impedance state and defined logic low or high states. Propagation delay TPLH. This is the time delay between specified voltage points on the input and output waveforms with the output changing from low to high. Propagation delay TPHL. This is the time delay between specified voltage points on the input and output waveforms with the output changing from high to low. Figure shows the two types of propagation delay parameter. It is defined as the average transition delay time for a signal to propagate from input to output when the binary signals change in value. The signal through gate take a certain amount of time to propagate from the inputs to output. The interval of time is defined as the propagation delay of the gate. Propagation delay is expressed in nanoseconds and 1 nanosecond is equal to 10 raised to minus 9 of a second. The signals traveling from input to output of the system pass through number of gates. The propagation delay of the system is the sum of the propagation delays of all these gates. When the speed of operation is important, each gate must have a small propagation delay and the digital circuit must have minimum number of gates between input and output. Figure of merit. Speed power product. The speed of a logic circuit can be increased, that is, the propagation delay can be reduced at the expense of power dissipation. We will recall that when a bipolar transistor switches between cutoff and saturation, it dissipates the least power but has a large associated switching time delay. On the other hand, when the transistor is operated in active region, power dissipation goes up while the switching time decreases drastically. It is always desirable to have a logic family low values for both propagation delay and power dissipation parameters. A useful figure of merit used to evaluate different logic family is the speed power product expressed in picojoules, which is the product of the propagation delay, which is measured in nanoseconds, and the power dissipation per gate measured in milliwatts. For example, an IC has an average propagation delay of 20 nanoseconds, average power dissipation of 5 milliwatt. So, the speed power product is 100 picojoules. Noise margin. Noise margin is related to ability of the logic gate at the input to accept or reject the signal at logic 1 or logic 0. This is termed as noise immunity. Noise immunity of a logic circuit refers to the circuit's ability to tolerate the noise voltages on its inputs. A quantitative measure of noise immunity is called noise margin. They are defined by VNH and VNL. Typical values of noise levels. Difference between the worst case output voltage of one stage and worst case input voltage of the next stage. Greater the difference, the more unwanted signal that can be added without causing incorrect gate operation. Typical acceptable voltage ranges for a TTL logic family are as shown. A logic gate with an input at voltage level within the intermediate range will produce an unpredictable output level. Noise margin here is 2.5 volt minus 0.8 volt, that is equal to 1.5 volt. Noise margin and noise immunity. This is the quantitative measure of noise immunity offered by the logic family. When the output of the logic device feeds the input of another device of the same family, a legal high logic state at the output of feeding device should be treated as a legal high logic state by the input of the device being fed. Similarly, a legal low state of a feeding device should be treated as a legal low logic state by the device being fed. We have seen in the earlier paragraphs, while defining important characteristic parameters, that legal high and low voltage levels for a given logic family are different for output and inputs. Figure shows the generalized case of legal high and low voltage levels for output. As we can see from the two diagrams, there is a disallowed range of output voltage levels from VOL max to VOH min and an intermediate range of input voltage levels from VIL max to VIH min. Since VIL max is greater than VOL max, the low output state can therefore tolerate a positive voltage spike equal to VIL max minus VOL max and still be a legal low input. Similarly, VOH min is greater than VIH min and the high output state can tolerate a negative voltage spike equal to VOH min minus VIH min and still be a legal high input. Here, VIL max minus VOL max and VOH min minus VIH min are respectively known as low level and high level noise margins. Evolution of logic families. As mentioned in the earlier sessions, logic families are fabricated using basic components like resistors, diodes, transistors and MOSFETs. Let us consider the basic logic circuits used in earlier logic families consisting of only diodes and transistors. Let us start with the basic logic family, that is DL, diode logic family, as shown in the figure. In this logic circuit, diodes D1 and D2 and resistor R is fabricated in a single IC. A and B are inputs and Y is the output of the circuit. If A equal to 0 and B equal to 0, that is logic 0 and logic 0, then both diodes D1 and D2 are forward biased and output Y is equal to 0 volt, that is logic 0. When A is equal to 0 and B is equal to 1, or A equal to 1 and B equal to 0, then either of D1 or D2 is forward biased, thus making the output Y is equal to 0 volt, that is logic 0. However, if A and B both are logic 1, then both the diodes D1 and D2 are reverse biased and output Y is equal to logic 1. Hence, this circuit represents logical AND operation, that is Y is equal to A and B. Figure shows the truth table of this logic circuit. Resistor transistor logic. In this circuit, transistor is off if any one of the inputs A or B is at logic 0. That is, A is equal to 0 and B is equal to 0. This is because base emitter junction would be reverse biased. Hence, output Y is equal to logic 1. When both inputs A and B are at logic 1, then the transistor would be on and the output Y is at logic 0. Hence, this circuit acts as a NOR gate, that is, Y is equal to A or B bar, that is a NOR gate. Figure shows the truth table of the circuit. Diode transistor logic. In this circuit, diodes and transistors are fabricated on a single chip. When both inputs A and B are at logic 0, then diodes D1 and D2 are forward biased and transistor is off. This is because the emitter base junction of the transistor is reverse biased and hence output Y is at logic 1. Hence, if one of the input is at logic 0, output Y is at logic 1. On the other hand, if both inputs A and B are at high logic level, then diodes are reverse biased and transistor is on and the output is at logic 0. Thus, this circuit behaves like a simple NAND gate, that is Y is equal to A NAND B. Figure also shows the truth table of the above circuit. Summary. Now let us summarize the module. In this module, the importance of using logic families, now let us summarize this module. In this module, the importance of using logic circuits in the form of digital ICs is discussed. One has to consider the logic circuits as number of basic components fabricated on the single chip. Depending upon the components used in the fabrication, the logic digital ICs are classified into number of families like TTL, CMOS, ECL, etc. One has to use the same logic family for designing different logic circuits in order to avoid the complexity in the circuit design and compatibility in the main issue. Let us summarize the module. This module explains the importance of different logic circuits in the form of digital ICs. One has to consider logic circuits as number of basic components fabricated on the single chip. Depending upon the components used for the fabrication, the logic digital ICs are classified into different families like TTL, ECL, CMOS, etc. One has to use the logic family for designing the logic circuit in order to avoid complexity in the circuit design as well as compatibility is the main issue. Different characteristics of logic families like noise margin, propagation delay, figure of merit, etc. are also discussed in detail and they are also defined in detail. Importance of these parameters in the design of digital circuit is analyzed, which is referred as the figure of merit. This decides the performance of logic IC family. Lastly, evolution of logic families was explained considering basic logic circuits like DL, RTL, DTL, etc. This is the end of module for characteristics and types of logic families. We will discuss different logic families in detail in the next modules.